So what we're going to do next is we're going to look at the ANOVA table. What this is telling us overall is our F statistic is probably the first most important thing. So 34.11, what that's doing in the ANOVA table is it's converting that to a p-value. And then ultimately what this says is because our p-value is well below 0.05 and even 0.01, we can reject the null hypothesis that all coefficient or all regression coefficients except the intercept are equal to 0. So what it tells us then is that at least one predictor is contributing meaningfully for explanatory power. Rarely if I run a regression in which I don't find this statistically significant, at least somewhere, like at that point, you just know that there's something off, either in the coding, you might have a column shift, something that's just completely off about it. But for the most part, you're going to pretty well know whether or not something's off. If you do find out that significance marker is not coming up and you've got something pretty significant in some kind of error in your data. So the regression sum of squares here, 327, going down this list. So that's the variability in GPA explained by your model, whereas the residual sum of squares of 985 is the variability that's left unexplained. So the total sum of squares is 1312. So what this is nothing more than a stepwise function of explaining how we got to our R square up here, because what it's doing is it's taking the amount that we explained relative to the amount unexplained. So it's taking that 327 and dividing 1312 and creating that 249. So that's where that R square value is actually coming from. So ultimately, do you really need to interpret the regression residual sum of squares? No, really not, because you're going to get that out of the R square value. So for the most part, it's a feature of noise. But that said, it is helpful to see the magnitude of the sum of squares and how they come up. Add to it, so the degrees of freedom are going to show us that out of our regression, we have DF of 14, which is the number of predictors that we have. So instead of having to go through and count, we can look at the degrees of freedom and say, okay, with their 14 degrees of freedom within their regression, this is the amount explained. That's the number of explanatory or predictor variables that we have. And then the 1438 is taking that total base of n and subtracting the number of predictors and then minus one. It's basically the calculus behind how this whole thing works. So what this table is not going to tell you, and this is worth noting, is it's not telling you which predictors are significant, which is what we're going to get down to the coefficients. So all it's simply telling us is that the model taken as a whole is what it is. It's statistically significant, and it's showing us how that we arrived at that R square value, and then also the number of variables that we have to work with here. So in plain English, we might say that with an F statistic of 34.11 and the p-value below 0.05 or below 0.01, this regression model significantly improves our ability to predict first-year GPA compared to using no predictors at all. So I would hope so. So then saying roughly 25% of GPA variation is explained by this set of predictors.